In a gaseous diffusion enrichment plant, the solid uranium hexafluoride from the conversion process is heated in its container until it becomes a liquid. The container becomes pressurized as the solid melts, and UF6 gas fills the top of the container. The UF6 gas is slowly fed into the plant's pipelines, where it is pumped through special filters called barriers, or porous membranes. The holes in these barriers are so small that there is barely enough room for the UF6 gas molecules to pass through. The isotope enrichment occurs because the lighter UF6 gas molecules, made with uranium-235 atoms, tend to diffuse faster through the barriers than the heavier UF6 gas molecules made with uranium-238. One barrier certainly isn't enough, though. It takes many hundreds of barriers, one after the other, before the UF6 gas contains enough uranium-235 to be used in reactors. At the end of the process, the enriched UF6 gas is withdrawn from the pipelines and condensed back into a liquid that is poured into containers. This UF6 is then cooled and solidified before it is transported to fuel fabrication facilities where it's turned into fuel assemblies for nuclear power reactors. All this sounds very nice, but I want you to get an idea of how freaking big and complicated these facilities are. Let me take you through a series of steps showing how the diagrams of the enrichment plant become more and more abstract until only the details we want to think about are included. This is what a gaseous diffusion unit really looks like, much like a great big stainless steel drum. This isn't particularly useful. If we could look inside it, it would look something like this. The feed stream brings UF6 to one side of the barrier, and some fraction of it diffuses through the barrier, and the rest exits and becomes the depleted stream. The gas that diffuses through the barrier is slightly enriched in U-235 and becomes the enriched stream. These stages are put together one after another to form what is called a cascade. Our next step is to draw the stages as boxes with a feed stream and two exit streams. These exit streams become the feed streams for the other stages in the cascade. Now let's look at stage N in the figure showing the cascade. And let's begin to put some math to things. The enrichment factor, or stage separation factor, is called alpha, and it's defined as follows, where alpha is the ratio of the relative concentration of 235 in the enriched stream divided by the relative concentration of U-235 in the depleted stream. Let's look at this carefully, because I want you to understand what all the little symbols mean here. See stage N in the figure above. Y sub N are the atoms or moles or molecular concentration of U-235 of the enrichment side of the stage. That means that 1 minus Y sub N is the atoms or moles or molecular concentration of U-238. Likewise, X sub N is the atoms or moles or molecular concentration of U-235 on the depleted side of the stage. In words, this enrichment factor, alpha, is the ratio of the relative molecular concentration, U-235 divided by U-238, in the enrichment stream leaving the stage, divided by the relative concentration of the depleted stream leaving the stage. Now let me teach you to think as an engineer thinks. We're going to do something called material balances. If we draw a huge ring around the whole cascade system and look at the goes-inas and the goes-outas, we know at steady state these must balance. Looking at the number of moles in the feed, the number of moles in the product, and the number of moles in the waste, we see that the feed must equal the waste plus the product. We can also look at the feed product and waste streams and do a balance on the uranium-235. The equations for these two material balances are F equals P plus W, product plus waste equals feed. The feed times X sub F is equal to the product times X sub P plus the waste times X sub W, where F is the number of moles fed into the cascade, P is the number of product moles, and W is the number of waste moles. X sub F, X sub P, and X sub W are the mole fractions of the individual streams. Let us suppose, as is usually the case, that the feed is natural uranium containing 0.711 atom percent of uranium-235. Let us suppose that the waste stream contains 0.3% of U-235 and the product contains 70 atom percent of U-235. For each mole of product, how much feed is needed? Can you work this out? Hit the pause button and go work it out. Hey, it's easy. 2 equations, 2 unknowns. Okay, I get 169.6 moles of feed for each mole of product. What did you get? There's a lot more to understand about cascades than these 2 simple balance equations, and that's an understatement. Let's take a balance across A prime in the figure and find the net flow between stages in the cascade. Looking at the figure, we can write L times Y sub n is equal to L minus P times X sub n plus 1 plus P times X sub P. If we further suppose there's no mixing of streams that have unequal concentrations of uranium-235, we have something called an ideal cascade. In symbols, this last statement is translated of Y sub n is equal to X sub n plus 2. And from the definition of alpha, we get this equation. I could spend an hour and help you derive all these equations, but let's not. I'm just going to tell you that by taking these equations and making some simple assumptions, we can show that the number of stages needed to get a particular enrichment is given by the equation here for N ideal. We can also show that the interstage flow rates vary at each stage. That's going to make things complicated, right? And they are given by L ideal is equal to this formula for the enriching stages of the cascade and equal to this formula for the stripping part of the cascade. The equations we've looked at so far are good for any cascade process. Now let's look at some real examples to give you an idea of how big a project it is to enrich uranium, particularly for gaseous diffusion plants. For gaseous diffusion plants, the enrichment factor can be assumed to be near 1.0043. Why this odd number? From molecular mechanics, we know that the ratio of the speeds between 2 gas molecules at the same temperature is S1 over S2 is equal to the square root of the masses of the inverse ratio. For U-235 and U-238 hexafluoride, the ratio of their respective molecular weights are 238 plus 6 times 19 divided by 235 plus 6 times 19, where the 6 times 19 is the 6 fluorine atoms times their molecular weight of 19. This ratio is equal to 1.0086. Therefore, the ratio of speeds is the square root of this, or our famous 1.0043. To understand why this sort of works, if we could arrange a very small tube so the 235 and 238 would race down this tube, the 235 would win. And this is basically what our barrier pierced by these very small holes does. And the enrichment across the barrier is 1.0043, theoretically. In practice, it's smaller than this. But let's use this number for our examples, and let's make sure you understand the equations that I gave you above. Let's let P, our product stream, be 1 mole, and let the final enrichment be 80%. Let the final waste stream concentration, otherwise known as the tails, be half of the input feed enrichment, or 0.00355%. Now, find the feed and tails needed to produce 1 mole. Okay? Next, how many enrichment stages do we need? And how many stripping stages? Let me help you and say that the negative number that you get for the stripping stages is correct. In this formula, negative means it's part of the stripping section. Finally, and here's the surprising one, what is the interstage flow rate at the feed stage? For an ideal cascade, that's kind of a surprising number, isn't it? And it's even more surprising if I sum all of the interstage flows over the whole cascade. There are over 34 million moles of gas pumped around for each mole of product. Good grief. How these plants are laid out is roughly defined by the interstage flow curve above. If the final stage is 1 diffusion unit, then the feed stage is 51,805 units hooked in parallel. And yes, these plants are that big. They are freaking monsters. The one operating plant in the United States is at Paducah, Kentucky, and sits on a 3,425 acre site, containing 750 acres inside the security zone. One process building covers 74 acres, and there are 4 process buildings. The peak power capacity is 3,040 megawatts, and the largest process motor is 3,300 horsepower. To cool the processes, the site uses 26 million gallons of water a day and has approximately 400 miles of process piping. There are 19 miles of roadway in the site and 9 miles of railroad. It's a big place.